The time has come to enter Chapter 7 of the dark art of linear algebra, wherein you will be introduced to the mysteries of Eigenstuff. In short order, you will meet eigenvectors, eigenvalues, eigenspaces, and eigenbases. What are all these strangely named things with this cryptic German prefix, eigen? Well, if you consult a German-English dictionary, you will find that eigen tends to be translated as something like characteristic or typical or something like that. And while such translations may work reasonably well for ordinary German, they don't really quite convey the flavor of what's going on in linear algebra, where eigen has an almost magical quality, which I suppose is why we tend not to translate it, and we end up with these German-English bastard words like eigenvalue or eigenbasis. But if I were forced to come up with some sort of English meaning that conveyed what eigen was all about in linear algebra, I would propose something like essence revealing. The eigenstuff of a linear map or matrix reveals to us, in some sense, the geometric essence of that particular linear transformation. And you'll see what I mean as we come to define each of these individual eigenterms. So let's jump into that process by defining eigenvectors and eigenvalues. We'll make two definitions at once. A non-zero vector v is said to be an eigenvector of a linear map T, or a matrix A, if TV is lambda v for some scalar lambda. Or if we are working with a matrix A, then the statement, of course, would be AV is equal to lambda v. And the scalar lambda, when this happens, is called an eigenvalue of the linear map, or matrix as the case may be. And to be a little more precise, we would say that lambda is the eigenvalue of T corresponding to the eigenvector V. All right, those are our first few definitions, but much remains to be discussed, such as, what are these things, geometrically speaking? Why should we care about them? And how do we find them? Well, we will address the first two concerns in this video, though the second one, why we should care about eigenstuff, is something you will come to understand more and more the further you go into linear algebra. But the third question, how do we find eigenvectors and eigenvalues, is something that for the most part, I'm going to push off until a later video, because until we have a feel for what these things are and why we should care about them, I don't want to get bogged down in computational details. In a lot of linear algebra courses, immediately after defining eigenvectors and eigenvalues, they immediately dive into the question of how to compute such things, and as a result, people end up just doing weird computations, memorizing procedures, without really understanding what it is they are doing or why they should be doing it in the first place. I don't want that to happen here, which is why I'm pushing off the computations until we're comfortable with the basic meaning of eigenstuff. Okay, so let's handle the first question. What are eigenvectors and eigenvalues viewed geometrically? Well, this is easy to see from the definitions themselves. Let's say I've got a linear map defined on R2, so from R2 to itself. And let's call our linear map T. So if I have any vector v in R2, when I apply the linear map to the plane, the vector v gets mapped somewhere else in the plane to TV. Now, just based on my little picture here, I can ask the question, is vector v an eigenvector of the map T? Well, v is a non-zero vector. It would be an eigenvector of T if its image under T is some scalar multiple of itself, which, according to my picture, is clearly not the case, because any scalar multiple of v, of course, lies on the line that v itself lies on. So vector v is definitely not an eigenvector of T. On the other hand, maybe we have some other vector w, such that when we apply our linear map T, w gets mapped to this vector tw, which actually does lie on the line that vector w itself lies on. This looks like T of w is, maybe 3w. So vector W is indeed an eigenvector of the map T with eigenvalue 3. Similarly, if we were working, say, in R3 and had a linear map defined on it, or let's say a 3x3 matrix representing such a linear map, let's call that matrix A, then if we have some vector U such that when we hit it with matrix A, it becomes this guy, which is minus half of U, then vector U is an eigenvector of matrix A with eigenvalue of minus 1/2. So I think you can see already what the geometric meaning of an eigenvector is. No vector is an eigenvector full stop. It's always an eigenvector relative to some mapping or some matrix. To say that some vector is an eigenvector of a mapping or matrix is simply to say that that map or matrix simply scales the vector, either in a positive sense, as it is here, or in a negative sense, as it is here. But in both cases, the original vector is simply being scaled by the map or matrix. Any such vector is an eigenvector, and the stretching factor, the scaling factor, is the corresponding eigenvalue. Let's do one last little visual example. Suppose that I have some non-zero vector z, and when I hit it with the matrix A, it gets mapped to the origin. Can I say that z is an eigenvector of A? Well, let's see. Does it satisfy the definition? It needs to be a non-zero vector. Well, it's definitely a non-zero vector. And when I hit it with the map, we'd need to get a scalar multiple of the vector itself, which we do, because of course we could write the zero vector as 0 times the vector z. So vector z is indeed an eigenvector of A with eigenvalue 0. And in fact, I can guarantee that z is not going to be the only eigenvector with eigenvalue 0. How can I be so sure? Well, let's stop and dwell here for a while, because doing so I think will lead us in a very natural and nice way to the notion of an eigenspace. But let's not get ahead of ourselves. And speaking of space, I need some, so I'm going to get rid of this definition, assuming you already have it in your notes, and of course it's in the book. That's better. Let's put this in a nicer location, and now we can return to my claim, which was that z cannot be the only eigenvector of A with an eigenvalue of 0. How do I know this? Well, some basic linear algebra vocabulary practically leads us by the nose to this fact. After all, what does the matrix A do to vector z? It kills it. It sends it to the origin, to 0, which means that vector z lies in the kernel of A, because the kernel of A, by definition, is the set of all vectors in R3 that get mapped to the origin. And one of the most important things to know about the kernel is that it is a subspace, in this case of R3. And what do we know about the subspaces of R3? Can there be a subspace of R3 that consists of a single non-zero vector? No, of course not. The only subspaces of R3 are the origin itself, lines through the origin, planes through the origin, and the entirety of R3. And that's it. So the kernel has to be one of those. And we know it's not just the origin itself, because after all, here's a non-zero vector that lies in the kernel. So that means the kernel is at least one-dimensional. It's either a line, a plane, or all of R3. And no matter which one it is, it consists of infinitely many points, all of which, by definition of the kernel, get mapped to the origin, which means that every vector in the kernel, well, strictly speaking, every non-zero vector in the kernel, is an eigenvector of matrix A, with eigenvalue 0, right? To spell this out, if k is any vector in the kernel, any non-zero vector in the kernel, because we want it to meet the definition of an eigenvector, then ak is the zero vector by definition of the kernel, and the zero vector itself can be rewritten as 0 times the non-zero vector k, but then ak is 0k, so k is an eigenvector of A, since A maps it to a multiple of itself with eigenvalue 0. Good, so we've just concluded that every non-zero vector in the kernel is in fact an eigenvector of A with eigenvalue 0. So there's not just one vector that gets mapped to 0, there are going to be infinitely many of them. In particular, every vector on this line through the origin that contains vector z, this vector, and this vector, and this vector, they all must be eigenvectors with eigenvalue 0, because whatever the kernel of A is, it's a subspace, and the smallest subspace subspace it could possibly be would be a one-dimensional subspace, namely this line through the origin containing vector z. Now the kernel might be larger, it might be a two-dimensional kernel, in which case the vectors on this line would not be the only ones that are eigenvectors with eigenvalue 0. In fact, there would be a whole plane of eigenvectors of A with eigenvalue 0. A plane that contains this line as just one of its infinitely many lines. In fact, just to keep going with this theme, I know that this particular matrix has either a one-dimensional kernel or a two-dimensional kernel. We already said that it can't have a zero-dimensional kernel, namely the origin itself, because, well, we've already identified a non-zero vector in the kernel. But it definitely can't be a three-dimensional kernel. It cannot be the entirety of R3, because I have in my picture this other vector, u, and it does not get mapped to the origin. It gets mapped to minus half of itself. So if the kernel were three-dimensional, if the nullity of this matrix were 3, we could not have a vector like u. Rather, everything in R3, all of it, would collapse into 0. Yet here's something that doesn't, so for the sake of the argument here, let's just go ahead and assume that the kernel is this line through the origin. But whatever it is, we know that every non-zero vector in the kernel is an eigenvector of A with eigenvalue 0. So the set of all those eigenvectors put together is almost a subspace of R3. The set of all eigenvectors with eigenvalue 0 falls short of being a subspace only because it does not have the origin, since we defined eigenvectors as non-zero vectors. I will explain why we did that shortly. But if we take all the eigenvectors with eigenvalue 0 and then just throw the origin in with them to form a set that in this case would consist of that entire line, we would have a genuine subspace of R3. And we would call it the eigenspace corresponding to the eigenvalue 0. Or more briefly, we will abbreviate that with the symbol capital E sub 0. Capital E for eigenspace, 0 because this is the eigenspace corresponding to the eigenvalue 0. And at this point, you could be forgiven if you objected that this is totally superfluous terminology. We already have a name for this thing. It's the kernel of A. Why give it a second name? Well, we do this because it turns out that every eigenvalue of a map, not just eigenvalue 0, but every eigenvalue that a map has an associated eigenspace. And usually we don't have special names for those. So we do need a new name for them. Well, I've just made a very strong claim, so I'm going to need to back that up with some justification. So let's stick with our picture here and think about this other eigenvector we looked at, u, which matrix A maps to minus half of u. So this was an eigenvector whose eigenvalue was minus a half. And you know what? Let me change the name of that a little bit. Instead of calling that vector u, I'm going to call it u sub 1 for reasons that will be clear very soon. So we know that minus 1/2 is an eigenvalue of the matrix A. And I claim that u sub 1 is not the only eigenvector with that eigenvalue. That in fact there is an entire subspace, an eigenspace, full of eigenvectors with eigenvalue minus 1/2. Let's just fumble along and see why this is so. First of all, suppose we take some scaled version of vector u1, like this guy, which I'll just call c times u1. C could be anything. It could be positive, it could be negative, it could be large, it could be small, whatever. It can therefore represent any point on that line. Well, I claim that it too must be an eigenvector of A with eigenvalue minus 1/2. Why is that so? Well, let's sketch it out over here. What do we know about A times CU1? Well, by one of the basic linearity properties of matrix vector multiplication, we know that the scalar can be pulled through the matrix, giving us C times AU1. But we already know what AU1 is. That is going to be minus 1/2 of U1. And we know by basic properties of working with vectors that we can rewrite this as minus 1/2 times CU1. So the net effect of applying A to our input vector CU1 is simply to take that input vector and scale it by minus 1/2. So CU1 is indeed an eigenvector with eigenvalue minus 1/2 for any non-zero scalar C. Good. So that means that every point on that line that contains U1, our known eigenvector, is also going to be an eigenvector of A with the exact same eigenvalue, -1/2. Again, strictly speaking, the 0 vector is not an eigenvector, but we're ultimately going to throw it in with all the eigenvectors to plug the hole and fill out an entire eigenspace. But wait a second. Okay, so all those vectors are going to be eigenvectors with eigenvalue 1/2. But could there be some other ones? Maybe there are more eigenvectors with that same eigenvalue to be found. Well, yes, there might be. I like to think of finding eigenvectors as almost like mining. You're hunting around for them, but once you find an eigenvector, you're in luck, and you're going to find an entire vein of eigenvectors, namely an eigenspace full of eigenvectors. So having found U1, we've discovered, we've got this rich vein of eigenvectors in here. Might there be more around? Well, there might not be, but if there are, like let's just say that we have some other vector that we find that is not in the span of U1, and it too is an eigenvector of matrix A with eigenvalue -1/2. So let me go ahead and call that one U2, and let me clean up some clutter here. Much better. Well, if U2 is an eigenvector with eigenvalue -1/2, we know where it's going to get mapped. Back here, its direction is reversed, and its length becomes only half of what it was before. Now, we've already seen that the entire span of U1 lives in the eigenspace corresponding to the eigenvalue -1/2. By the same logic, every vector in the span of U2 is going to be an eigenvector with eigenvalue -1/2. But it's better than that. Every linear combination of these two eigenvectors will be another eigenvector with the same eigenvalue. That's easy to see with a quick computation. If we start with any linear combination of these two eigenvectors with the same eigenvalue, -1/2, and hit that linear combination with matrix A, the basic linearity properties tell us that this is going to be C times AU1 plus D times AU2. But we know what AU1 and AU2 are, because those are known eigenvectors. Namely, we know that this stuff is equal to this stuff. C times -1/2 of U1 plus D times -1/2 of U2. And with a little algebraic manipulation of the usual vector operations, which we established all the way back in chapter 1, we know that we can factor the -1/2 out of both terms and rewrite this stuff as -1/2 of CU1 plus DU2. So at the end of the day, feeding our linear combination of the two known eigenvectors into the matrix A gives us that same linear combination scaled by -1/2. So our linear combination is therefore an eigenvector of A with eigenvalue -1/2. That means that every vector in the span of these two eigenvectors which share eigenvalue 1/2, in other words, any vector that lives on the plane that they determine, is going to be an eigenvector of the matrix A with the eigenvalue -1/2. Or strictly speaking, all the non-zero vectors in the span are eigenvectors, because the zero vector itself, which of course is in the span, is not considered an eigenvector. But if we throw that zero vector back in the set, that plugs the hole, and we get a full subspace of R3, which of course we call capital E sub -1/2, the eigenspace corresponding to the eigenvalue -1/2. So in this case, we had a very rich vein of eigenvectors. That first one we found, U1, ended up being the harbinger of a whole plane's worth of eigenvectors. And now you might ask, well, could there be more? I mean, maybe there's a third eigenvector that's linearly independent of U1 and U2 that also has eigenvalue 1/2. Should we go searching for one of those? Well, no, we don't have to, because we know there can't be one, or we can deduce that there can't be one. Because if there were one, what would happen? Well, by the same argument we had over here a minute ago, it would follow that every vector in the span of U1, U2, and some hypothetical U3 would also be an eigenvector with eigenvalue 1/2. But the span of three linearly independent vectors in R3 is, of course, all of R3. So that would mean every vector in R3 would be an eigenvector with eigenvalue -1/2. But we know that's not true. We're staring at Z, for example, which we know has eigenvalue 0. The same vector can't be an eigenvector with respect to two different eigenvalues, because then what would it mean? Z simultaneously gets scaled by -1/2 and gets scaled by 0? Well, that doesn't make any sense. It has to be one or the other. So we we know that our hunt for eigenvectors with eigenvalue minus 1/2 must be complete. This is the complete set. Still, you might ask, well, maybe there are some other eigenvalues of our matrix A anyway. I mean, here are the vectors with eigenvalue 0, and here are the vectors with eigenvalue minus 1/2. Maybe there's some other vector out there that gets stretched by 5 or something like that. Could that be the case? Well, actually, that could not be the case. And let's think about this and see why there can't be some other vector out there which is an eigenvector of the same matrix, but with eigenvalue 5 or 19 or whatever, something that's not 0 or minus 1/2. And thinking about this will actually lead us to our fourth important eigenconcept. We are working in R3. Well, we know there are lots of different bases of R3, the standard basis, I, J, and K, and infinitely many others. But we're actually staring at a very special kind of basis, a basis that consists exclusively of eigenvectors. And I'll bet you can guess what we call such a basis. That's right, we call it an eigenbasis. So in this case, let's let crazy B be the eigenbasis consisting of U1, U2, and U3. To be more precise, I should say that B is an eigenbasis of R3 relative to the matrix A, consisting of U1, U2, and Z. To be an eigenbasis just means that it's an ordinary basis, except that all three of the basis vectors are eigenvectors relative to some particular map or matrix. There's nothing deep about the definition itself. It will have very nice consequences, though, as we'll see soon. But for now, let's just get to know it bit by bit, approaching it cautiously and getting to know it before we ultimately embrace it. Okay, we've got this eigenbasis. So what? Well, it can help us explain an assertion I made a moment ago, which was that I can't have any other eigenvalues for this matrix besides 0 and minus 1/2. Like there can't be some other vector out there that gets stretched by a factor of 5. How can this eigenbasis help me see why such a thing would be impossible? Well, think about what a basis, never mind the eigen business, just think about what a basis does. It gives us coordinates for any point in the space. That is, for any vector in the space. And we can understand how a linear map affects any such vector if we know how it affects the vector's individual components in the directions given by the vectors in the basis. So if I have some other vector v out there, I know that v is some unique linear combination of these eigenbasis vectors. In fact, v is going to be alpha u1 plus beta u2 plus gamma z for some scalars, alpha, beta, and gamma. And those scalars just tell us how many u1 steps, u2 steps, and z steps we have to take from the origin to get to the tip of vector v. Okay, that comes just from knowing that our three vectors make up a basis. Well, what happens if I hit v with matrix A? Well, I get A of all that stuff, and now, by the miracle of linearity, knowing what a map does to the basis vectors tells us what it does to every vector. You know how it works. Linear maps, and hence matrices, preserve linear combinations. So if our given vector was alpha u1 plus beta u2 plus gamma z, its image under the matrix A is alpha times u1's image plus beta times u2's image plus gamma times z's image. And if those individual images of the components were all being scaled by the same thing, well then the vector itself would be scaled by the same thing. But its components are being scaled in different ways. Its u1 and u2 components are getting scaled by minus 1/2 when they get hit with A. But its z component is getting scaled by 0. So since the components are being scaled by different values, the vector is getting jerked around in different ways. So it gets pulled off the line on which it lies. And we don't end up with just a plain old stretched version of it. It's as if along two axes of our basis, vectors get stretched by minus 1/2, but along the third axis, it ruins that simple stretch because vectors get stretched by 0. In other words, they get killed. And if we wrote this out numerically here, we would get minus 1/2 of alpha u1, the first component of our vector, minus 1/2 of beta u2, the second component of our vector. So those two components got scaled by 1/2, but then plus 0 of gamma z, our third component. So although it might initially have looked like the vector was being stretched by -0.5, that only happened to the first two components. The third component got stretched by something entirely different, 0 in this case. But even if it had been a different eigenvalue, if it had been 42, it would have been stretched by 42 instead of -0.5, meaning that overall the vector is not being stretched, or scaled, I should say more broadly. And that's the idea. For any vector in R3 that does not happen to lie in one of the two eigenspaces, that vector will of necessity have some components, or at least one component, that gets stretched by a factor of -0.5, and another component that gets killed, stretched by a factor of 0, meaning the vector can't simply be stretched. So eigenbases are nice. When we have an eigenbasis, we can understand the map or matrix as a sequence of stretches along particular axes. And as a result, if we can write down the matrix of a linear transformation relative to an eigenbasis, the matrix will be very, very simple. I'll show you what I mean. Let's suppose that our matrix here, A, was the matrix representation of some linear map T relative to the standard basis, whose vectors I have just drawn in here in green. Good old I hat, J hat, and K hat. Now we know from our previous work in chapter 6 what this matrix would look like. It would be a 3x3 matrix whose columns are the images of the standard basis vectors expressed in standard coordinates. But figuring out what those look like numerically, well, would be impossible given the information I have in my picture. We could maybe make a very crude estimate, but it would be a pain. For the first column, for example, we'd have to say, well, where does I hat get mapped? Well, I don't know, but I could break it down into a U1 component, a U2 component, and a Z component, and I know that the U2 and U1 components get multiplied by -0.5, and the Z component gets killed. You put all that together and then figure out roughly where it lies, and then try to figure out how many I steps, J steps, and K steps I have to take to get there, but that would take a long time, and at the end of the day, well, we've just got some 3x3 matrix. Who knows what it looks like? Some scramble of 9 numbers. But on the other hand, if we were to try to write down the matrix representation of our transformation relative to our eigenbasis, B, that is a different story altogether. That's going to be very easy, and it will look very nice, because again, we know from chapter 6 the basic form. That's going to be a 3x3 matrix whose columns are the images of the B basis vectors, our eigenbasis basis vectors, with their coordinates written relative to our eigenbasis. That might sound like a mouthful, but if we think about what it actually means, we'll see that this is going to be a very simple matrix. Take the first column. Okay, what's T of U1? Well, I don't have to do anything fancy here. Here's U1. T of U1 is this guy, which I know is -1/2 of U1. Okay, so T of U1 is -1/2 of U1. Well, if I want to take the vector -1/2 of U1 and express it in B coordinates, I just have to think how many U1 steps, U2 steps, and Z steps do I need to get there? Well, obviously, I take -1/2 U1 step and I'm done. So my coordinates relative to the eigenbasis will be -1/2 for my -1/2 U1 steps, 0 for my lack of U2 steps, and 0 for my lack of Z steps. Good. What about the second column? T of U2. What's that? Well, here's U2. Oh, that's an eigenvector with eigenvalue -1/2. So T of U2, well, that's just this vector, which of course is -1/2 of U2. Okay, so there it is. What are its B coordinates? Its coordinates relative to the eigenbasis? Well, it lies along one of the eigenvectors, U2. So to get there, of course, we take 0 steps in the U1 direction, -1/2 a step in the U2 direction, and 0 steps along the third axis, the Z direction. Well, that was easy. What about the third column? That's the eigenbasis coordinates of the image of Z. Well, the image of Z, that's an eigenvector with eigenvalue 0, so its image is the 0 vector itself. So, of course, that third column is just 0, 0, 0, because we don't have to take any steps at all to get to the origin. Now, this is interesting. This is not just some jumble of 9 numbers. Look at what we've got. On the main diagonal, we have our eigenvalues. We have -1/2, which appears twice, which corresponds to the fact that the eigenspace for the eigenvalue -1/2 has dimension 2. There are two linearly independent eigenvectors with eigenvalue -1/2. And then we have this 0, which corresponds to our other eigenvalue. And it only appears once because that eigenspace has dimension 1. And everywhere else in the matrix, below and above the main diagonal, we have nothing but zeros. Matrices like these are wonderful, and we call them diagonal matrices. We've had some homework problems about them, but a diagonal matrix is just a square matrix that has zeros both above and below the main diagonal. On the main diagonal, all bets are off. Those entries could be non-zero or 0, but that main diagonal is the only place in a diagonal matrix that any non-zero entries can live. And the moral of this story is that if B is an eigenbasis relative to a map T, then T's matrix representation relative to that eigenbasis is a diagonal matrix. There's more to the story, namely the diagonal entries will be the eigenvalues of the linear map, and the number of times each one appears will correspond to the dimension of that eigenvalue's eigenspace. I don't want to write all that down right here, but it's something you should understand. This is actually quite easy to understand once you have internalized all of the many definitions I have thrown at you so far in this video. I'll work through another example, but before I do that, I want to mention that this is not just a quirky feature. This is one reason we really like eigenbases. Diagonal matrices are very, very easy to work with. They have all sorts of nice algebraic properties, some of which we will discuss later. And from a computer science standpoint, they're great because when you do computations with diagonal matrices, there's not that much to do, which means it's very inexpensive, computationally speaking, to work with them. If you want to feel viscerally what I mean, write down a random 5x5 matrix with non-zero entries throughout, and then just multiply it by itself. It'll take you a little while. Then do the same thing, but let your 5x5 matrix be a diagonal matrix. You'll find that multiplying it by itself goes much faster when it's diagonal. More on that theme soon. But let's drop down a dimension to R2 and look at another example there, just so we have some practice with all this terminology and the consequences thereof. Okay, so here we are in R2, and let's imagine we have some linear transformation T from R2 to itself. This mapping will move vectors around in the plane, but let's say we happen to know two particular linearly independent eigenvectors. I will call them B1 and B2, and let's suppose that T scales B1 by a factor of half, so it shrinks it down to half its size, but still pointing in the same direction. And let's suppose that the corresponding eigenspace is this line containing the eigenvector, which I've labeled capital E sub 1/2. So that means every vector on this line gets scaled by a half. And let's suppose that B2 is an eigenvector whose corresponding eigenvalue is 3/2. So it gets scaled up by T to 50% larger than it was before. And as we discussed in our previous example, that will be the same situation for every vector on this line containing the eigenvector. And in fact, this line must be the entirety of the eigenspace capital E sub 3/2, because if there was some other vector in R2 that was also scaled by 3/2, then everything in the span of that vector and B2 would be scaled by 3/2, thanks to the linearity of T. But everything in the span of those two vectors is every vector in the plane. And we know that's not the case, because here's a vector in the plane that gets scaled by 1/2, not 3/2. Well, this is great, because I have two linearly independent eigenvectors, so they are eigenvectors that constitute a basis for R2. In other words, they are an eigenbasis, which I'll call crazy B, for R2 relative to the linear map T. So again, all that means is that these two vectors are a basis for R2, obviously, and they are both eigenvectors relative to the map T. So the map T merely scales each of these two vectors. We can think of these two eigenspaces as being like axes that are in a particularly nice position. Anything lying on either axis just moves along the axis when it gets hit by T, and anything not lying in either eigenspace will not be an eigenvector. But we can still understand it in terms of its components that do lie in those eigenspaces. Since it's easier to see what's going on in R2, let me spell this out in a little more detail on this example. Here's part of the grid determined by our eigenbases. Now let's consider a vector in R2. It does not lie in an eigenspace, so it doesn't simply get scaled by t, but what exactly does t do to it? Well, this green vector is not an eigenvector, but we can decompose it into a sum of eigenvectors, simply by sliding this point down the grid lines until it hits our eigenspaces, so that we end up with our green vector being the sum of these two yellow vectors, which are both eigenvectors because they live in the eigenspaces. So t of the green vector is t of the sum of the two yellow vectors, which by linearity is t of the first yellow vector plus t of the second yellow vector. So what does t do to this first yellow vector? Well, it lies in the eigenspace corresponding to 1/2, so it shrinks it down to half of what it was before, putting its tip here at this red dot. And what does t do to the other yellow vector? Well, it's an eigenvector with eigenvalue 3/2. So it grows by 50%, and it ends up right here. Now sum up the two vectors corresponding to those two red dots, and we end up right here. So of our original, more or less random vector in R2, one of its components gets scaled by 1/2, the other gets scaled by 3/2, and as a result, the image of the original vector does not stay on the same line. It is not an eigenvector. It gets pulled off in another direction. Okay, so again, we see why an eigenbasis is nice geometrically. It reduces the effect of a linear map to just some scaling along various axes. And algebraically, an eigenbasis is wonderful because the matrix representation of the linear map relative to which we have an eigenbasis is going to be diagonal. So in this case, for example, if we want the matrix representation of the map relative to the eigenbasis, of course, it's going to be a 2x2 matrix, and let's think about what its columns will look like. Well, the first column is the image of the first eigenbasis vector expressed in b coordinates. Well, the first eigenvector has eigenvalue 1/2, so it gets mapped to half of b1. So its b1 coordinate is, of course, 1/2, and its b2 coordinate is 0 because we don't take any steps in the b2 direction. And you should see how this worked out. We only get a non-zero entry in the first slot because to get to the image from the origin, we only travel in the direction of the first basis vector because it's merely getting scaled by t. Same thing's going to happen in the second column, except only the second slot can have a non-zero entry. Because what goes here? Well, it's the image of that second eigenbasis vector after it's mapped by t, which is going to take it to 3/2 of what it was before. It doesn't move at all in the b1 direction, only in the b2 direction. So to get to the image, we take 0 b1 steps and 3/2 b2 steps. And lo and behold, there is our diagonal matrix. And of course, the entries on the diagonal are t's eigenvalues, the scaling factors along the various axes of the eigenbases. And that's all that this map T does. If we wrote it in, say, standard coordinates, it might not be terribly illuminating. But when we have the matrix in coordinates given by an eigenbasis, we understand exactly what it does. Scales components in this direction by 1/2, scales components in this direction by 3/2. And that's it. But while we are here, I will mention one more bit of terminology. This particular linear map we've been looking at is said to be a diagonalizable linear map. It's an ugly term, but it means exactly what you'd think it means. To say that a linear map is diagonalizable is simply to say that it is capable of being represented as a diagonal matrix. Not every linear map can be diagonalized, because the statement I have right here can actually be strengthened a little bit. A linear map T is diagonalizable if and only if an eigenbasis relative to T exists. But alas, not every linear map admits an eigenbasis. So that means not every linear map is diagonalizable. To have an eigenbasis relative to a linear map, we need eigenvectors, and enough of them, enough linearly independent eigenvectors, to form an entire eigenbasis. We don't always have them, and we can see this with some very simple examples. The simplest example would be something like a 90-degree clockwise rotation of the plane around the origin. What are the eigenvectors of such a map? Well, it only takes a few seconds of thought to realize there are no eigenvectors of this map, because whatever vector vector you start with, when you hit it with a rotation, it ends up pointing at right angles to where it pointed before. So there's no way that it's getting scaled. Since our rotation has no eigenvectors at all, there's obviously not an eigenbasis for R2 relative to this rotation. There's not even a single eigenvector. So this rotation is not diagonalizable. There are all sorts of different ways to represent it with a matrix, but none of them will be diagonal because we don't have enough eigenvectors to form an eigenbasis. By the way, non-diagonalizable maps are sometimes called defective maps, which shows what low repute they are in certain quarters. Another simple example of a non-diagonalizable map is a shear. We worked with these frequently back in chapter 5 when we were talking about determinants. So let's think about the shear that is described by the matrix whose columns are 1, 0, and 2, 1. And this is the standard matrix representation of our shear, which I guess I'll call S. So I could describe this matrix as the representation of the shear relative to the standard basis. So our shear takes the standard basis vectors, I hat and j hat, and looking at the first column, it fixes I hat. It doesn't move at all, but j hat gets sent to 2, 1, like so. This shear determines the following grid, and it's not too hard to see that it has one obvious eigenspace. Everything on the horizontal axis is frozen by the shear. It doesn't move at all. So that is the eigenspace corresponding to the eigenvalue 1. And in fact, that is the only eigenspace. We're operating in a two-dimensional space, R2, but we only have one dimension worth of eigenvectors. Consequently, we don't have enough linearly independent eigenvectors to build up an eigenbasis relative to our shear. I mean, there are infinitely many eigenvectors, every vector on that line, but we need two linearly independent eigenvectors to have an eigenbasis since we are working in R2. Since we don't have enough linearly independent eigenvectors to get an eigenbasis, this shear is not diagonalizable. It's not too far from it. It's in a nice form already, upper triangular matrix, but there's no basis we can come up with that representing this shear with respect to that basis would give us a diagonal matrix because we would need an eigenbasis for that. Okay, I think you get the point. And you know, maybe now is a good time to come back to a old lingering question. Back in the beginning of this video, we said that a vector v is an eigenvector of a linear map T if two conditions were met. The second one, the core of the definition, is that T of v is lambda v for some scalar lambda. But there was this easy to miss condition as well, which was that to be an eigenvector, v has to be not the zero vector. We know that we can have 0, the scalar, as an eigenvalue. We saw an example like that earlier, but we don't consider the 0 vector an eigenvector. And the question is, why did we impose that condition? I mean, the definition of an eigenvector is a man-made thing. We could have left that out, right? Well, we could have, yes, but then we'd have a very awkward situation, because suppose we allowed the 0 vector to be considered an eigenvector. Then what would its eigenvalue be? I mean, think about it. A linear map does what to the 0 vector? As we all know, it sends it to the 0 vector. But I could rewrite the 0 vector as c times the 0 vector for any scalar c whatsoever. That means that, for example, 2 would be an eigenvalue of every linear map, because t of 0 is always 2 of the 0 vector. But also 73 would be an eigenvalue of literally every linear map, because t of 0, no matter what t is always going to be 73 times the 0 vector. And so, if we considered the 0 vector an eigenvector, we would be forced to conclude that every linear map has literally every real number as an eigenvalue, which would render the concept of eigenvalue useless, because eigenvalues actually tell us a lot about a linear map. I mean, if I have a linear map defined on R2, and I know that 2 is one of its eigenvalues, and 4 is another eigenvalue, then I know that the linear map is really just a transformation that scales things along two axes, 1 by 2 and 1 by 4. But if we didn't have this condition, and I said, oh, you've got a linear map on R2, does it have any eigenvalues? You'd have to say, why, yes, of course, like every linear map, every real number is an eigenvalue. And then suddenly I know nothing. So for that reason, we exclude the 0 vector from the ranks of true eigenvectors. Though, of course, we feel its loss in other ways, which is why when we write down a careful definition of an eigenspace, we have to say something like all the eigenvectors corresponding to a certain eigenvalue plus the zero vector. All those thrown together in a set make up the eigenspace. So it's a little awkward however you do it, but this is the way we have settled upon. You know, my original intention in this video was to end with the idea of eigendecomposition, but I'm afraid if I get into that, this video will reach an intolerable length. So I'm going to make that the topic of its own video, probably a fairly short one, which I'll do next. And instead I will end this one by looking at a computer animation or two that might help you see what's going on with eigenvectors, eigenspaces, and so on a little better, at least in the case of a map from R2 to itself. So I will see you over here at this nice website that I used in an earlier video all the way back in chapter 3 when I introduced linear maps for the first time. In case you missed that one or have forgotten, the idea is that the little green and red crosshairs that you see on your screen are like the targets to which our linear transformation that we're going to define shoots I hat, which is the green vector, and j hat, which is the red vector. The resulting linear map transforms the grid and is given by the matrix in the upper left corner. Never mind that yellow vector that is multiplying it on the right. I'll get to that in a minute. The important thing is that we can actually animate this linear map and see how it affects everything in the space. Very nice. Okay, now for that little yellow column vector, that just gives me a way to get a better feel for what's going on in the map by looking at some other vector in the plane, and then we can watch what the transformation does to it in particular. And for our purposes, notice that the vector, the yellow vector, gets dragged off of the line through the origin on which it originally lay. It gets pulled off of its span, so to speak, which means that that yellow vector clearly is not an eigenvector. It is not being scaled by this map. Something else is happening to it. And it's not obvious looking at the map if there are any eigenvectors. Well, a nice thing on this little website is that I can show you where the eigenvectors live. In this case, they live here. We have two eigenspaces in this case. Well, that's good. That means we could form an eigenbasis, which means we could diagonalize this map. But what I want you to see in this animation is what happens to those eigenspaces, or the vectors on those eigenspaces, when we run through the tape. So let's start that right now. Aha! They just get stretched out, just as we knew they would. That's what eigenvectors do. Here they are again, running through the map. Everything else is being dilated and kind of moved around in different ways, but everything on those two lines just gets stretched. So we really see how they serve as natural axes for this transformation, and why we can think of all this eigenstuff as showing something about the essence of this particular map. Let's see, is there anything else I want to show while I've got this thing up? Oh, sure, why not? Let's go back to that shear that we looked at a moment ago, which fixed I hat and mapped j hat to 2, 1. Now let's carry out the map. We just have the one eigenspace that we talked about before. The horizontal axis is fixed. It doesn't move at all because the eigenvalue is 1 there. And every other point in the plane we can see is having its direction changed. So, of course, our only eigenvalue is 1 in this case. Every other vector that is not in that eigenspace changes its direction. And since we don't have enough linearly independent vectors to make an eigenbasis, this shear is not diagonalizable. Okay, let's stop here, and in the next video we will not, as I originally thought, discuss how to compute the eigenstuff. Rather, we will devote some concentrated, unrushed time to the very important topic of eigendecomposition. In the book, I introduce this topic in a long exercise in the first section of chapter 7. So for now, you can go ahead and do all the other exercises in that section, and if you want to, you can hold off on the problem about eigendecomposition until after you have watched my video on that topic as well. Lucky you, you can just go watch it right now or very soon, whereas I have to actually make the thing. But, alright, I've got my work cut out for me. I know what comes next. See you then. Bye.